When a particle first enters Earth's atmosphere, it becomes a photon and receives a charge equal to E. We'll find the value of E in a moment. So photons have a charge, though they don't have mass. And when the photon becomes a particle, it has a mass of 1, and it also has a charge. So we need a way to account for this shift. We have two types of energy here, charge and mass. This is an electromagnetic charge and a biological mass. Let's find equations so we can observe the particle as it passes from purely a charge into a more of a biological mass. There's a law in physics called the law of conservation of energy, which says that the energy in a particle may change form, though the total amount remains the same. So let's come up with energy equations to compare the energy of a particle as it passes through three mediums, the air, the water, and a membrane. Let's fill in the parts we know so far. We know the mass of a photon is 0. Its charge is E, measured in centimeters. It's measured as a wavelength. Let's form an equation with these two pieces of information. If we multiplied them together, the equation would be 0. However, if we added these two together, the value of the charge would be preserved. So let's say the total energy of a photon in air is equal to centimeters plus grams. So we have the wavelength measured in centimeters and the mass measured in grams. Electromagnetic plus biological energy. Then the photon splashes in the water. When it first lands in water, its mass is 0, and then it incrementally increases to 1. So we'll need two equations, when the mass is close to 0, and then when the mass is close to 1. When the light wave hits the water, it refracts into two parts. So we can say we have two branches, each with a length measured in centimeters. So our equation could read centimeters squared plus g. And we could say this is for both equations when the mass is 0 and the mass is 1. When the light wave forms into a measurable unit, we have another equation. It's like now the mass separates into three dimensions, length, width, and height, as volume. And the volume is equal to 1. So we can cube the wavelength and multiply it times the mass. So here we have three mediums, and we have three equations to observe a light wave as it forms into a particle. Let's now find the value of the initial wavelength. Let's mark 2 points in space. Let's mark one as the tube floating near Earth, and the other as a point that can be where we come from, somewhere in space. We're not sure the exact path of the light wave, though we can estimate its trajectory. Even if it made all these tiny movements going all which ways, we can zoom out and see the particle's trajectory appear as a smooth curve between these 2 points. So let's estimate the length of this smooth curve. Let's use geometry to estimate this length. We could say that the shortest distance the wave could have traveled would be a straight line, or a diameter of a circle, with a value of 2 times r. The longest distance it could have traveled would be a semicircle with a length of pi times r. So let's say r is 1, so the length would be somewhere between pi and 2. One strategy to find the middle of something is to find the average. So let's find the average of these lengths and see if it can come up with a value of our wavelength. This would be pi plus 2 divided by 2. This equals 2.57, about 2.6. This is equal to E, measured in centimeters. This is sort of a value that we give to photons upon arriving on Earth to account for the long journey through space that they just made to arrive here. And this value is consistent throughout each energy equation. So we can fill in this value to each equation to determine the slow shift from electromagnetic energy into biological energy as the particle forms. And lastly, let's talk about speed. Speed is distance over time. Since we have values for the length of a light wave in different mediums, we can now determine the speed in which the light wave travels. To do this, we can say speed equals centimeters over time. In this case, time can be 1 second. It could be anything. Here, let's say it's a second. So we can say the particle travels about 2.6 centimeters per second in air, between 1.3 and 1.6 centimeters per second in water, depending on its density, and about 1.38 centimeters per second in an oil membrane. So we have the speed of light in air, 2.6 centimeters per second, speed of light in water, between 1.3 and 1.6 centimeters per second, and the speed of light in an oil membrane is about 1.38 centimeters per second. We're used to the speed of light being a large number. This is the speed of light in a vacuum. Here, we're relating the speed of light as it moves through the air, the water, and a membrane.